Good morning, good afternoon. I'm very pleased to join this conference, the Tissue Conference, and I will be talking about strategies in the development of smart fibers. My name is Orlando Rojas, and I'm coming from University of British Columbia in Vancouver, Canada. So, Professor Gonzalez asked me to introduce the topic of smart fibers, and the first thing that I did was to check the definition. And here you can see one of the definitions that are accepted. It's a material that can react, for example, to light and heat. And you may wonder what this has to do with tissue paper or with wood fibers. And I think there is a lot of. For one thing, lignocellulose fibers are an untapped bioresource. You can read in the top the different functionalities, complexities, also the fact that fibers are interactive, especially, for instance, with water, and are arranged in a multi-scale hierarchical and also comprising many different elements or compounds. Therefore, what we try to do is to utilize the properties that are inherent to wood fibers or plant fibers in general. And some of those are listed in the bottom. They can be strong, responsive, resistance, for instance, to heat and chemical stimuli, can be tunable, biodegradable, and sustainable. So I ask if you can think about any other material that has such combination of properties, especially comparing wood fibers that is carbon that is alive, for instance, against fossil carbon that has no function, has no structure, at least as it is found in nature, in the biosphere. So indeed, we can create materials that are smart, that are responsive using fibers. And for that, of course, one of the features that we want to exploit is the fact that wood fibers are multi-scale and hierarchical. This is best shown in this plot on the left, where we have different levels of deconstruction of wood fibers. From top down, we start with the millimeter size fibers, and by fibrillation, we go down the scale into macro, micro, and nano fibrillar cellulose, and we end up with the cellulose biomolecule. And of course, we realize here that as we go in the size scale, the challenge for processing and therefore the cost is going to be increased. And that relates to the deconstruction, the size, or the refining ability, or the severity of the refining. Now, what we find here is that, in fact, as we will learn later during this tissue conference, is that many of the physical properties of wood products will depend on this level of deconstruction. That's a topic that Professor Pollack will discuss in one of his short courses on paper physics. And also, as this is discussed in by other speakers, the fractionation is extremely important in this endeavor. If we think about tissue products, from the bottom right, you can see a recent reference that is quite useful. We're going to find that tissue products, especially those that we find around us, toilet tissue, facial, hands, towels, napkins, are really going to fulfill a number of properties that you can see as strength, the wet strength, softness, absorbency, and also brightness and color. And all these properties will depend on this degree of the construction. So now we can start to see the importance of, for instance, micro and nanocellulose as far as the development of properties in the future tissue papers. And that means that if we know how to use this deconstruction level, we can add value, we can add performance to the products. And that means that new properties may emerge beyond those that are listed in the bottom right. And that means that we can add to paper products some functions that relates to tactile properties, bioactivity, sensing, and interaction. That last one is, in fact, what I mean is communication, the ability to transfer data. So maybe my talk is a little bit out of the box, and we're conscious here that this will add cost to tissue papers, but in the future I can foresee that there is an opportunity in more advanced materials that are very lightweight. And for that reason, I have split my remaining of the talk into smart fibers in 3 parts, as far as those that correspond to the response to light management. And for that, we're going to use bleached and unbleached microfibers. Also, the fibers that will be deconstructed in such a way that we can play with additional properties like tactile and energy. And finally, surface modification of fibers. And here I will show 4 examples, including bioactivity, wear strength, multifunctionality, and sensing and communications. And these are the related to the ones that I showed in the previous slide. So starting with the smart fibers, as far as light, here you can already see that one of the properties that is important to consumers is the color, the brightness, the opacity of actually paper products is pretty important. And one interesting finding in this area is the possibility of using nanotechnologies to exploit the whiteness and brightness of the structures. And of course, this has a very close relationship with fiber physics. That is how the fiber network scatters light. And one interesting component here that is actually of recent data is the separation of microcelluloses in different lateral fibril size. And by using simply centrifugation, maybe you can think on different other techniques for fractionating fibrils by size. We can then obtain different populations of fiber width or diameter, from the finer ones on the left to the coarser ones on the far right. So here we have lignin-free fibers, bleached fibers. In this particular case, a very high level of fibrillation or deconstruction. We can think about this as a cellulose nanofibrils or microfibrils. And already we can see that the scattering in the aqueous suspension will be quite different depending on the fibril dimensions, thinking that these are all at the same concentration. And that, of course, has to do with light transmission, light scattering. And here we have a typical equation that looks into the effect of, for instance, the scattering mean free path and diffusion behavior of the material. Not only in suspension, but when they are forming a network such as paper. And this reminds us of other theories that are very typical to paper makers, such as the Kubelka-Munck theory of light absorption and light scattering. My point here is to report about how these fibrils that are produced can be placed into a two-dimensional film or a nanopaper in this case. And those nanopapers, as you go from top down, they can be extremely transparent, so top left, to extremely opaque, bottom right. And those papers are produced from the same basis weight. On the far right, you can see the networking structure of the fibrils, going from the finer ones on top down to the coarser ones. And that would be a plain view together on the far right with a cross-section of the material. And already here you can appreciate that the fact that light scattering is so different for these different materials is because the type of entanglement between the fibers and the porosity is quite different, and that can be controlled by fractionation. So my point so far is fractionation is extremely important for paper products, and I would say that this also includes tissue paper. And already here we are seeing the case of smart fibers in the sense that we can control light transmission and light scattering. This can be further developed into, for instance, developing color And this is a fact that is very well known for cellulosic nanomaterials, in particular cellulose nanocrystals, that in suspension form this type of arrangement called chiral nematic liquid crystals in suspension. And when a suspension of those crystals is dry, then the system is collapsed into a film that produces selective light reflection with very interesting colors and effects such as iridescence. So this is also illustrated on the right. The case of different garments and materials that can be coated with this type of structural color using the arrangement of cellulose nanomaterials at the interface. So it's an interesting sort of development, not only in the production of whiteness and brightness, but also in fact color. And this can be actually quite easily done in the case of all cellulose materials. Now, if we turn our attention to the case of lignin-containing fibrils, I think we can pretty much arrive to similar conclusions. So here we're looking at size fractionation, the same way that I explained for lignin-free fibers, but in this particular case with high yield fibers. And we go from very fine fibrils that come from the same fiber source, but just by the fact that we're doing fractionation, we find that the amount of lignin in those finer fibrils is actually higher than those that are of medium size or the coarser ones. So there is a relationship between lignin concentration and fibril size when we take a population of fibers that are processed by the same unit, by the same source material, just that we fractionate in sizes. So there is a correspondence between fibril size and lignin content, as well as the molecular weight of the lignin. And this is quite interesting because I think this is a fact that we can use, we can exploit for many different purposes, including coatings, and in this particular case, to manage light scattering. In fact, with this lignin, or with these lignin-containing fibrils, we can produce very lightweight papers that will have completely different porosity. As you can see here, the ones on the left have a porosity of 40%. The ones on the far right, the finer ones, we have much smaller porosity. And this is explained by the arrangement of the fibrils in space, as we discussed earlier. And the roughness of the papers will be quite different. You can see the values in the bottom of the atomic force microscope images that are here. So the courses, of course, we have higher roughness. The finer the fibers, lower roughness, but also lower the porosity. And that means that we have here a way to leverage the property of the fibril fractionation by size to produce lightweight materials, paper materials, with different light scattering, different color, and of course different absorbency because the porosity is quite different. On the right, you can also see how the light transmittance can be quite different. In the case of the papers produced by the fine fibers, there is a more transparent structure. In the case of the coarser fibrils, then we have an opaque material. And this all relates, in fact, to the physical properties of the network. So when we look at scattering, we're also seeing here different properties that can be developed from the paper structure. And this is something that is already being considered. Here I show one joint work with our colleagues in North Carolina State University, where we have been looking into the use of micro and nanofibrillated cellulose from recycled fibers to produce papers. And in this case, as a bulk addition, I think it made a lot of sense because those fibrils provided the possibility to produce stronger networks at a lower basis weight. But beyond that, there are other properties that we need to keep in mind, and those are illustrated in this figure on the right, where the fibrils can be introduced so that we can print materials, we can do 3D printing objects, or we can produce self-stamping films. And here, in the case of lightweight paper materials, the important thing to say is that those lignin-containing fibrils can have very interesting properties. For instance, antioxidant, UV protection or shielding, and also very important here, anti-fouling properties or protein repellency properties. And these are things that are, in my mind, still far from being exploited, meaning using the natural composition of fibrils to produce this type of functionalities. Let's take a quick look about energy and tactile management. And in this particular case, it's very interesting that there are some liquids or solid materials that when melted, then absorb energy, latent heat of fusion. And that means that these materials can really then, upon the reverse effect, when solidified, can release that heat. So that heat absorption or heat release can be quite interesting, because if we tune the heat of absorption to the given temperature of utilization, then we can have a material that allow us to control the temperature. But here I propose that this type of materials, called phase change materials, and examples include, for instance, polyethylene glycol that is used in some paper making products. They can also be used, for instance, to change the feeling of the material when we place our fingers on the tissue. You can also think about other phase change materials that can bring other different properties, including an scent, a color, or a given other property. So combining this fact that we have something that can change the phase behavior depending on temperature, I think I propose at least that that can produce an interesting property in the fibers that are placed in a paper network. Okay, in the last part of my talk, I would like to refer to the case of smart fibers by surface modification. And what I want to do is to walk through 4 examples that are current in our research as a way to illustrate the development of smart fibers that perhaps can find use in tissue products. So the surface modification that I will talk here can be quite large in the range of possibilities. Here I put just a list of typical modifications that have been developed on cellulose, and that includes the absorption of surfactants, the use of proteins and amphoteric molecules, polyampholytes, including proteins, the deposition of polyelectrolytes as a single layer or as a multi-layers, the use of complexes. I will show an example of a complex, or also the deposition of nanoparticles. In this example, I list quantum dots, carbon dots, or, as I will show, lignin particles, and then also the use of amphiphilic glycopolymers. Finally, surface grafting, I will give an example, and the development of bioactive cellulose. So this is just a list of different possibilities, and I will only show four of those examples as an illustration to engineer smart fibers. The first one is to actually take advantage of a natural property of a polyphenol molecule that exists in trees, especially in the bark, tannins. And those tannins can have very interesting properties that can be highly appreciated in different tissue papers, tissue products. For instance, the antimicrobial properties, antiviral properties nowadays will be quite relevant of tannins, make these molecules quite interesting as an additive in paper products. And here, the possibility is quite interesting if we think about doing the fractionation that I explained before, the refining and the deconstruction of the fibers into micro and nanofibrils by grinding, for instance, or by extensive refining. It is possible then to add tannins as an additive in that process. And in that particular case, what we have found is that tannin can reduce the energy that is consumed in the grinding or in the fibrillation. So we combine the two products, small amounts of tannins, and then we produce fibers that can retain the tannins. However, one thing that we notice is that the tannins are difficult to stay with the fibrils. They will be washed out. They won't be retained. And for that reason, what we have used as an optional pathway is to combine this also with surfactants. So by using a small amount of surfactants, we can have a better binding of the tannins on the fibrils, and then we can produce a paper product that can exhibit the effects of the tannins, and why not, those of the surfactants that we're adding in the process. So on one hand, we reduce the energy of fibrillation. On the second hand, we're going to develop a functional property in the tissue paper or the paper product that is being produced. And this, of course, has an important implication, not only in the anti-inflammatory, antiviral, and antimicrobial properties that I have explained before, but also in the possibility to block UV irradiation. In the second case, I explained the development of wet strength. And here I once again use a natural polymer, either chitin or chitosan, deacetylated chitin, chitosan. And this is an option that has been explored in paper making. And in fact, chitin and chitosan products have been used in the past in paper making. And here I just highlight in this slide the fact that the use of this type of additives is quite demanding if you think about the different conditions that they need to sustain and the very narrow window of operation as far as the consistency, temperature, and pH, and properties or conditions in processing like low conductivity and the fact that we want to minimize the cost and has to be water-based and minimize capital investment. These are really very challenging situations. Nevertheless, I want to say that in this particular case, chitosan products fare quite well as a paper making additive. In particular here, what we have found is the possibility of using chitosan to increase the tensile strength, both the dry and especially the wet strength. And for that, of course, we can use chitosan alone, but in this figure that I'm showing here, I indicate the case of chitosan alone, also with soy proteins and with dialdehyde starches. And that last combination was really the one that produced a really great performance, not only as far as the dry strength, but also as far as the wet strength, that, as you know, is a very important property in the case of tissue papers. Another example of the bulk addition of chitosan is that the possibility that chitosan can form complexes with cellulose, especially if cellulose is oxidized. And that will produce materials that have or display very high wet strength. And also of particular value is that besides the wet strength that develops, also antibacterial properties can be seen. And my colleague Lokendra will be talking about this topic. In this particular case, I think it's important to mention the fact that we can either use the chitosan in the bulk, or as was proposed in his group, the idea of using chitosan together with cellulose nanocrystals as a material that can be sprayed on top of the tissue paper to reduce or avoid or limit at least the bacterial growth. In the same sense, I would like to share with you this very recent paper from our work where we mix cellulosic fibers with chitin microfibers, in fact, and that combination allows us to nucleate the growth of lignin. So essentially what we did here, you can read the details in the paper, but nevertheless, was to take lignin in solution, add it to the system, and then the chitin fibers that were mixed with the fibers allow for the nucleation of the lignin into nanoparticles. And by electrostatic interactions, then we have at the end fibrils that were coated with lignin nanoparticles, very small in size. And these lignin nanoparticles, similar to what I explained earlier for tannins, can be quite interesting because then with these lignin particles, we develop antibacterial properties. So it's a very inexpensive way to nucleate, to produce lignin particles in the system from a fully integrated process where the nanotechnology of lignin can be exploited to produce these functional properties, in this particular case, UV absorption or UV shielding, and also antibacterial properties. The third example has to do with the possibility also to nucleate other types of molecules into metal organic frameworks, and this can be done by the so-called biomineralization process. And as an illustration here from our work, is the idea here is use nano and microcelluloses that are mixed with given precursors, in this particular case, zinc ions that can be placed in solution with methyl imidazole to produce a metal organic framework. And that happens extremely fast. In the presence of cellulose, these frameworks that you see in the bottom at the center will be formed. And these structures are quite interesting because they are cages that are hollow and can allow us to, for instance, encapsulate given chemicals or to release given functionalities. The point with these different metal organic frameworks is that we can design and integrate them in the suspension to produce fiber products that can be endowed with the properties of the metal organic framework. In particular, you can see here the example of those materials that are formed in situ extremely quick. And if we look into an image, you can see the very small dimensions of these cubic structures that are formed. And these structures, these metal organic frameworks, are known for different possibilities. For instance, in storing small molecules, in the absorption and releasing of bioactive materials, including also gases, in cleaning, or in the preservation of given bioactivity. So once again, the idea here is the utilization of metal organic frameworks in lightweight materials to bring new functionalities to the otherwise non-functional fiber products. Finally, the last example that I want to share is that of the communication, sensing and communication. And for that, one of the requirements is that the paper product needs to be hydrophobized. In general, we want to make patterns on the surface of the fiber or in the whole paper so that we can have water repellence in this particular case, but we can also make this spatial resolve, as I will explain in the next slide. The point here is that by a modification that involves the installment of a vinyl group, we can then link or couple a thiol-terminated molecule, a hydrocarbon, for instance, with a vinyl unit, and that binding can be activated by UV irradiation. So this is a so-called click UV activated click coupling or click reactions. The beauty of this reaction in this particular case, where this is activated by UV irradiation, is that we can, for instance, produce first a number of different functionalities on the surface of the paper. We can think about alkyl paper, hydroxyl, carboxyl, amino, PEG paper. PEG is the one that I have earlier discussed. So different functionalities can be very easily activated on the surface of the paper by the UV click. And that click can be done in such a way that we can control where the activation occurs. So by using a photomask that can screen the UV or the areas where the UV light should go, then we can do the modification in given spaces. For that reason, I was talking about a spatial resolve activation slide where you can see tracks of hydrophobic and hydrophilic areas on the paper that is produced. Now, why to do this? The main idea here is to have a paper substrate that can be produced in such a way that we can install given devices. In this particular case, for instance, a sensor that is connected to an antenna and a printed battery, so that we can have an autonomous system where we can do sensing and at the same time transmit or communicate via an antenna, wireless, and all this powered by a printed battery, or alternatively also with an electrochromic display. And of course, this is a very advanced material, but I don't see an issue about thinking of future tissue papers that can at least incorporate some of these very inexpensive devices that can be actually cellulose based. For instance, the idea of sensing is a quite important one. And this sensing idea here can be used, for instance, to look into the cold chain or to sensing or detecting given molecules, etc. So it can be quite important and relevant to advanced paper products. This is coming from a project that we have under the European Union Horizon 2020 program, and these are some of the partners that are working in this area. And in this particular case, we're targeting regular paper products, but what I propose here is that in a not so far future, also tissue papers can be considered for similar functionality. Anyway, this was my last example, and I hope here that I was able to bring this idea that first reducing in size fibers, or at least fractionating fibers, doing the engineer of the size of the materials can allow us to fine-tune the physical, mechanical, and optical properties of lightweight materials. And from that, then, to produce smart fibers that can find many applications as the ones that I explained in the previous slide. And in the future, of course, this is going to be quite important because I would say that the current forest products will, of course, continue to be very important over the years. But if we think about the value of production, we need to think about new value-added products. And some of the functionalities that I introduced today should be considered in this type of possibilities for the future. And this has been actually well planned in some efforts in different countries, especially in this particular case I put here, the case of Finland, where a flagship, a cluster of research where we're involved is aiming to this type of new value-added forest products in the future. With that, I would like to finish acknowledging my research group members, the FinCERES cluster that I just mentioned in Finland, and also the Bioproducts Institute in University of British Columbia. Thank you very much.